Okay, now we are moving on to section 2.7 to 2.9. As you see, the title of this section is called Thermochemistry. Thermochemistry is the branch of thermodynamics which studies heat transfer during chemical reaction. If you recall the previous sections, we got to know about the enthalpy. For constant pressure process, enthalpy change corresponds to heat transfer, right? And you want to calculate the amount of enthalpy change for various types of changes, physical change, chemical changes, etc. And from those changes, we'll also introduce Hess law. I believe that you guys have learned this from general chemistry class, okay? And to do that, we need to introduce a new physical concept, which is called standard states. Okay, we'll got to know that, and also we'll learn a few more basic concepts about this enthalpy change. And finally, we'll get to know how we can calculate the amount of enthalpy change when the temperature changes. Okay. So let's move on. So as I mentioned, thermochemistry is the branch of thermodynamics. We are basically learning thermodynamics, okay? And especially thermochemistry deals with heat transfer during chemical reaction, okay? As you all know, during chemical reaction, heat could be either produced or absorbed, right? The reaction that produces the heat during the reaction is called exothermic reaction, right? So for exothermic reaction, Q is negative, right? On the other hand, endothermic reaction is a reaction in which that heat is observed by the reacting system. Okay. So, in the case of endothermic reaction, Q is positive. Okay. Since exothermic reaction produces heat by reacting system, the temperature of the system is higher right after the reaction than initial, right? That's obvious. In chemical reaction, the system is something like reaction vessel plus the chemical contents which are involved in this kind of reaction. Okay? So after exothermic reaction, temperature increases. Okay? So heat must be transferred from the system to the surroundings in order to return the system to its initial temperature. Because the temperature has been increased for the system to make the same temperature, same initial temperature, heat must be transferred from the system to the surroundings. And the opposite case can be applied for endothermic reaction. Okay? As we learned in previous sections, these reactions can be described in terms of enthalpy, especially for constant pressure process. So, when chemical reactions occur, there will be enthalpy change, right? And the amount of enthalpy change will depend on many different factors. How many reacting contents are present, temperature, pressure, etc. Right? And depending on those various conditions, this enthalpy change will be different, right? It'll make problems complicated. So we need some reference. Okay? So to describe enthalpy change, we define a standard enthalpy change, denoted as delta H naught. Here this side represents standard states. Okay? So standard enthalpy change is the change in enthalpy where initial and final substances are in standard state. Standard state. What is standard state? Standard states, the definition of it is pure form of a substance at specified temperature at 1 bar, one specific pressure. Okay? So for example, standard state of liquid water at 298 Kelvin is pure liquid, right? At this temperature, at this pressure, H2O, water, exists as liquid. That's the standard state of water at these conditions. Okay? So, when initial and final substances involved in the chemical reaction are in standard states, then the enthalpy change during that reaction is standard enthalpy change. Okay, let's see an example. How about standard enthalpy of vaporization, denoted as delta VAP H naught. Okay. It's basically standard enthalpy change during vaporization. Okay. For example, for water H2O, if liquid state water vaporizes to vapor state, gas state H2O, there will be enthalpy change, right? And the enthalpy change, this physical change occurs at 373 Kelvin, right? Or 100 degrees C, and 1 bar, right? Specific pressure. So both of initial and final substances are in standard state. Okay. So we can define standard enthalpy of vaporization, which has some number. Okay. So the standard enthalpy change can be reported at any temperature, specified temperature, but usually, conventionally, we use 25 degrees C, 298.115 Kelvin. Let's first consider the enthalpy change of physical change. Okay. Physical change means phase transition, such as vaporization, fusion, melting, something like that. So, for these kind of physical changes, we can say those changes as standard enthalpy of transition from one phase to another, denoted as delta TRS H naught. Okay. Similar to what we have done for vaporization, you can do the same thing for other physical changes, melting, fusion, etc. And since enthalpy has interesting properties, we can easily calculate this enthalpy change of transition. The first one is enthalpy is a state function. You remember that internal energy is a state function, right? And the definition of enthalpy was H equal U plus PV, right? U is state function, P, pressure is state function, V, volume is state function. So enthalpy is also a state function, which means that it is independent of path between initial and final states. So, for example, if you know the standard enthalpy change of melting and boiling from solid to liquid, from liquid to gas, if you know the information about these two, you can easily get the information about enthalpy change of sublimation from solid to gas by simply summing up these two. Right? It's very simple. Okay. Also, since it is a state function, delta H naught differs only in sign for forward and reverse processes. Okay. So if we have information about condensing from gas to liquid as minus 44 kilojoules per mole for water, the standard enthalpy change of boiling of water from liquid to gas would be same number but different sign. which is well depicted in this diagram. Okay. Here shows the standard enthalpy of fusion and vaporization for various materials or elements. Okay. Although we only considered common transient physical changes such as fusion, vaporization, sublimation, there are also other types of physical changes, but we are not really interested in those things. Okay. All right. How about chemical change? Same, we are assuming standard states for both initial and final substances. Okay. Instead of physical change, we are basically doing chemical reaction, right? Chemical reaction. So we call the standard enthalpy change of chemical reaction as standard reaction enthalpy, or denoted as delta R reaction, RH0. Okay. So basically we are dealing with this kind of chemical reaction in which all of these reactants and products are in standard states. Okay, and we can get information about standard reaction enthalpy. Okay. Then how can we get this information? How can we calculate this standard reaction enthalpy? What information do we need to calculate this? Actually very simple. For example, let's consider this kind of reaction. 2A plus B goes to 3C plus D. This is the chemical reaction. And we want to calculate the standard reaction enthalpy for this reaction. All we need to know is the enthalpy, molar enthalpy of each of these species, because enthalpy is a state function, right? Since enthalpy is a state function, all we need to know is enthalpy of reactants and products. Okay? So if we know the enthalpy of A, B, C, and D, which is denoted as this molar enthalpy, then we can simply calculate standard reaction enthalpy by using this quantification, right? Here, this constant nu represents the stoichiometric coefficient, such as 2, 1, 3, and 1. Okay? So simply we sum up the enthalpy of products and we subtract sum of standard enthalpy of reactants, like this. Okay? It's easy. Okay? Then, how can we know this? How can we determine molar enthalpy of A, B, C, and D? Okay? Let's skip this part first. We want to know the molar enthalpy of each of these reactants and products. How can you know? It's actually easy. Those molar enthalpy of each species is called standard enthalpy of formation. Why? To determine this, or to determine the molar enthalpy of each species, we need some reference point, right? We want to know delta H, enthalpy change. There should be some reference point, some reference date, which correspond to enthalpy of 0, right? Then we can determine the change of enthalpy from that 0, the reference date. So what we do is that we want to determine the molar enthalpy of each species, okay? Then we just do this. We are doing standard enthalpy. We are basically calculating standard enthalpy of formation, how much enthalpy change to make those species, those chemicals, from its substituents. Okay? What it means is that we are, for example, from this kind of reaction, we want to determine the molar enthalpy of each of these species, CH4, O2, CO2, H2O, right? Then we just calculate how much enthalpy changes to make this compound, CH4 in gas state, from its components. Here components means C, carbon, H, hydrogen. In the case of oxygen, gas, O, oxygen atom is the component, right? CO2, carbon and oxygen, H2O, hydrogen and oxygen. Okay? So basically we make these compounds from its component atoms, and the important thing is each component, those components are in reference state. There's another definition. Reference state is defined as the most stable state of an element at the specified temperature and 1 bar. And at reference state, enthalpy is 0. We just assume it. Okay? If the elements are in the most stable state at specific temperature and 1 bar, those elements have enthalpy of 0. Okay? So, since we have reference point of enthalpy of 0, we can determine the enthalpy, standard enthalpy of formation to make those compounds. Okay? For example, let's consider this compound, C6H6, which is benzene, actually. If you want to know the standard enthalpy of formation of this compound, you simply divide this compound into its component, C and H2. Why we do that? Carbon is most stable as solid at 1 bar and at 25 degrees C. Solid is the most stable state. Okay? And hydrogen at 1 bar and 25 degrees C, hydrogen exists as gas, right? Gas is the most stable state for hydrogen. So their reference state with 0 enthalpy. Then we can determine the standard enthalpy of formation. Okay? How about nitrogen? Nitrogen. We want to calculate the standard enthalpy of formation for nitrogen. Nitrogen. The component of nitrogen is nitrogen, right? And the most stable state of nitrogen at 1 bar at 25 degrees C is nitrogen as gas. Same, right? So the enthalpy, standard enthalpy of formation for nitrogen is 0, just 0. Okay? Simple. Okay? So, that's it. If we have information about standard enthalpy formation for each compound, reactants, and products, we can determine the standard reaction enthalpy. If you have information about standard enthalpy of formation for products and reactants, we can easily determine the standard reaction enthalpy. Then how can we know these numbers? They are usually given. If you look at the textbook, like at the end of the textbook, appendix, there are huge tables with these numbers for each compound. Okay, so you can just look it up, put a number here, calculate the standard reaction enthalpy. Okay. We skip Hess law here. So it should be simple. Hess law is actually the result of enthalpy's property as state function. Since enthalpy is state function, only initial and final states are important, right? Okay. So the standard enthalpy of an overall reaction is the sum of the standard enthalpy of the individual reaction. That's obvious, right? If we have information about standard reaction enthalpy of this reaction as minus 124 kilojoule per mole, this reaction minus 2220 kilojoule per mole, this reaction plus 286 kilojoule per mole, then we sum up these three reactions. If you sum up these three reactions, we get this reaction. Okay? And the standard reaction enthalpy of this reaction would be same as summing up these three as minus 2058 kilojoule per mole. That's so simple, right? Because enthalpy is a state function. Okay? Group contribution. To determine the standard enthalpy of formation of specific compound, what we did was to break it as component atoms. Okay? Using the reference state. Okay? But it is sometimes difficult to exactly thermodynamically break enthalpies of formation down into contributions from individual atoms and bonds. What this means? Okay. Meaning of this is something like this. Let's see an example, actually. Let's look at this. If you want to know about the enthalpy of the contribution of each atom or bond for the enthalpy, standard enthalpy of formation, let's see these two compounds. These gray circles are carbon, so C, 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 C. Okay, so it has C, C single bond, 4 of them. Okay, this compound has 3 carbons connected to each other and 2 hydrogen atoms, right? 2 C, C single bonds, 2 C, H single bonds, and the contribution or bond formation of this C carbon-carbon single bond would be different between these and these compounds, right? The environments are different. Here, C, all 4 of them are same, right? But in this case, there are 2 hydrogen atoms, so it would affect the bond of these 2 C single bond. Okay? Since this is the case, depending on the connections, depending on the bond, the contribution of each atom or each bond would be different, right? We need to consider that. That's the group contribution, or we call it Benson thermochemical groups. Okay. So, let's see an example. Okay. Here shows the contribution at the standard enthalpy formation for different form of bonds, right? if there are 4 carbon-carbon single bond as shown here, the standard reaction enthalpy to form this is plus 8.16 kilojoules per mole. On the other hand, for this case, CH2C2 like this, to make this from its component, carbon and hydrogen, the reaction enthalpy change, standard reaction enthalpy is minus 20.7 kilojoules per mole. It's quite different, right? So from this information, with different group, different chemical structure, it has different standard reaction enthalpy. So from this information, we can estimate standard enthalpy of formation for any compound. For example, let's do it for hexane. Hexane has chemical formula of C6H14. Okay. So let's estimate the standard enthalpy of formation for hexane as gas and liquid at 298 Kelvin. If you look at the structure of hexane, let's see here. Okay. As you see here, it has 2 here and here, 2 CH3C group, the left side, the right side. Okay, and 4 CH2C2 group. 1, 2, 3, 4, right? So you sum up all of them. 2 CH3C, 4 CH2C2. 2 minus 42.17 here, plus 4 times minus 20.7. Then you get minus 167.1 kilojoules per mole as standard enthalpy of formation for hexane in gas state. Okay, so this is the information about gas. Okay. Then, if you want to calculate the standard enthalpy of formation for hexane in liquid state, you need to know about the standard enthalpy of vaporization for hexane, which corresponds to 28.9 kilojoules per mole. Then, by simply subtracting these two, you get minus 196 kilojoules per mole as standard enthalpy of formation for liquid state hexane. And interestingly, it's quite close to the experimental value for this number. Okay. All right. Finally, now we have learned how to calculate the standard reaction enthalpy, right? And for any type of chemical reactions, we can measure standard enthalpies at various temperatures. At different temperatures, enthalpy would change, right? Enthalpy would have different number. What if we have information about enthalpy change at a specific temperature? Can we easily calculate the standard enthalpy of reaction at different temperature? Yes, actually, we can do it using Kirchhoff's law as shown here. That's the result. First, the result shows something like this. If we want to know standard reaction enthalpy of specific temperature T2, we can determine this if we know the standard reaction enthalpy at T1 different temperature and information about heat capacity within these two temperature range. If we know both of these, we can easily determine this. Simple, right? Let's derive it. All right. Let's do the derivation for this Kirchhoff's law. It's very simple actually. Okay, let's consider chemical reaction. Actually, let's consider a very simple one. reactants is A changes to product B. Okay? And we want to calculate this enthalpy change of this reaction at two different temperatures. Okay? So we basically want to calculate and standard reaction enthalpy for same reaction at two different temperatures. First at T1 and T2 at two different temperatures. Okay? Alright. So let's call this reaction A to B at temperature T1 as reaction number 1. And this reaction, same component A, basically changes temperature from T1 to T2 as reaction 2. And this reaction as 3 from A to B at temperature T2, and this reaction as 4. Okay? Alright. As you see, the direction of arrows, you can determine this enthalpy change. Standard reaction enthalpy of reaction 1 should be equal to enthalpy change of 2 plus 3 plus 4, right? Because this is initial state, this is final state. You can follow this path or this path. Enthalpy as a state function should be same, right? Easy, right? Okay. So, enthalpy change of this reaction number 1 can be represented as standard reaction enthalpy at T1. This one is same as this one, and delta H2, the change of component A from T1 to T2, okay, this one can be described as T1, T2, Cp, A, dt. You remember from the definition of enthalpy, right? Cp, heat capacity at constant pressure, was defined as round H, round T at constant pressure. So we can write it like this. Okay? How about this one? Delta H number 3 is standard reaction enthalpy at T2. Okay? And this one, change of B from T2 to T1. T2 to T1, Cp, B. Okay, that's it. Okay, so if you rearrange it as function of this one, H T2 is equal to R T1 plus, if you combine these two integral, you get T1, T2, CPB minus CP A dt. Okay? That's all. As you see this slide, okay, this derivation actually is same as this one. Okay? Simple. Although I used very simple reaction from A to B, if the reaction is rather complicated, you can write this heat capacity as this, right? If you have information about heat capacities of reactants and products. And also if you have information about this reaction coefficient, stoichiometric coefficient, right? Then you can simply calculate this part, okay? So if you have information about reaction, standard reaction enthalpy of one temperature and heat capacities of reactants and products at this temperature range, you can easily determine the standard reaction enthalpy at different temperature, T2. Okay, this is the end of section 2.9. Okay, now we move on to the next, actually final sections of chapter 2, sections 2.10 to 2.12. The first law of machinery. Actually, this would be the most difficult part until this class, actually, in this semester. So we have learned first law of thermodynamics. Delta U is equal to Q plus W. We have learned how to calculate the amount of work for various expansion process, right? We also learned how to measure, how to determine the enthalpy, the amount of heat for constant volume or constant pressure processes. We have learned internal energy and enthalpy. Both of them are state functions. State functions have very interesting, useful properties, right? And we'll learn much more about that. Useful properties of state functions and derived relations and physical meanings of them. Okay? So in this part we'll deal with many mathematical derivations and expressions, etc. Okay? Especially you need to know about the differential equation. Okay? I believe that you have all learned about that before, right? Okay, then from those relations based on state functions of internal energy and enthalpy, we learn a bit more about useful relations or experimental results that are really interesting actually. We'll come back to that point later. Okay, it could be very fun. Okay, so let's do it one by one. State function. We have learned what state functions are, the definition, right? State functions are the properties that are independent of how the substance is prepared. The only important thing is initial and final state, okay? And examples of state functions include internal energy U and enthalpy H, okay? For this. On the other hand, there are other functions which are not state functions, which are called path functions. Path functions are functions that are dependent on the preparation way of the state, how they are prepared, or what paths they are following. Okay? The examples of path functions are we already know these: work and heat. You remember that depending on the processes, free expansion, isothermal reversal expansion, adiabatic expansion, etc., the amount of work and the amount of heat were different, right? That shows why these two functions are path functions. On the other hand, internal energy and enthalpy, if the initial and final states are same, these properties are same. Okay? Alright, so here shows the diagram same again and again about the state functions, right? If initial state and final states are same, the state function, the internal energy or enthalpy are same. Okay? But work or heat, which are path functions, they depend on paths. Okay? For example, if path 1 is adiabatic expansion, if path 2 is non-adiabatic expansion, for path 1, since it's adiabatic, Q is 0, but W is not 0, or could be 0, but generally it's not 0. But for path 2, since it is non-adiabatic, both Q and W are not 0. Okay? One thing interesting about these state and path functions, especially state functions, is that state functions, only initial and final states are important. So the change of state function, delta U or delta H, okay, can be expressed as like this, right? UF minus UI or HF minus HI, right? Similarly, if you use the expressions of differential, delta U can be expressed as integral from initial to final state du, right? It's the integration of differential, right? So, this differential form of state function du or dh are called exact differential. Okay? On the other hand, path functions q or w. For these two path functions, we never put delta, right? Because if you put delta U is UF minus UI, only depends on initial and final state, okay? But Q and W are not state functions, they are path functions, okay? So we do not put delta, it's just Q or just W. If you also express these path functions in using differential form, you can use same differential, integral from initial to final state dq, but these are path functions, so they depend on path, okay? And differential form of path functions, dq or dw, are called inexact differential. Okay, just that's the names, exact differential and inexact differential. Alright. Let's see an example to see if this is really true about state functions and path functions. Let's calculate. Consider a perfect gas in a cylinder with a piston. Initial state is T and Vi. Final state is T and Vf. Temperatures are same, right? Volume changes. It's basically isothermal expansion process. And let's calculate Q, W, and delta U for three different paths. Okay? The first one is free expansion against no external pressure. We already have learned this, free expansion. Second path is reversible isothermal expansion. We also learned this. Third path is irreversible isothermal expansion against constant external pressure. Actually, we have already learned this. We just reviewed them. Let's calculate it. You can calculate it actually. For path 1, free expansion, since there is no external pressure, W is equal to 0, right? Right? And since it is isothermal expansion for perfect gas, remember, for isothermal expansion of perfect gas, delta U is 0, right? Okay? For path 1, W is 0, delta U is 0. So, Q is also 0, right? From the first law of thermodynamics, delta U is equal to Q plus W, right? Okay? How about path 2? Same for delta U, right? Perfect gas, isothermal expansion, delta U is 0. How about W? We already have calculated this before, right? W is equal to minus nRT log Vf over Vi, right? And Q would be plus something, right? Plus nRT natural log Vf over Vi. How about path 3? Irreversible expansion. We have also learned this, right? Delta U is 0. How about W? W should be minus P external pressure times delta V. Okay, that's all. Very simple. Okay, so you can clearly see that For all these three passes, delta U is same, 0. But Q and W are all different. They are path functions. Okay. So I mentioned that there is something interesting about state function or exact differential. Exact differential is a differential form of state function, du or dh. Okay? And from very interesting properties of this exact differential, we'll see many mathematical functions, especially as partial derivative, like this. And those partial derivatives are very important. They have very interesting physical meanings. So for the following sections, we'll learn each of them. Okay? So to describe these state function properties, we are assuming a closed system of constant composition. So basically composition or number of moles are constant. Okay? N is constant. Okay? You remember from chapter 1 that there are 4 physical variables to describe the state of the state of system, right? Pressure, volume, temperature, and number of moles, right? And we fixed number of moles. So there are 3 variables remaining: pressure, volume, and temperature. Okay? So if we know any 2 of them, okay, pressure, volume, or temperature. Okay? No, let's say again, we have 3 variables: pressure, volume, and temperature. And since number of moles are fixed, okay, pressure, volume, and temperature should be related by a certain equation of state, right? And if we know any 2 of them, the third one would be automatically determined, right? Remember? Okay. Similarly, internal energy, which is also a physical variable which can describe the state of system, right, could be described as a function of these 3 variables: pressure, volume, or temperature. Excuse me. Okay. But since there are only 3 variables, if we know 2 variables only, that will be enough to describe the behavior of internal energy. Okay. So internal energy can be expressed as a function of 2 variables, either pressure and volume, or pressure and temperature, or volume and temperature, right? Either one is fine, but we select volume and temperature to describe internal energy. Okay? Okay, so internal energy as a function of volume and temperature. Let's say that volume changes small amount, dV. Temperature changes small amount, dT. Both of them changes to a very small amount that will result in a change of internal energy, small amount, right? du, right? Okay? Then how much internal energy changes as a function of volume or as a function of temperature? That will be expressed as derivative, partial derivative, right? Partial derivative of internal energy as a function of volume, partial derivative of internal energy as a function of temperature, when the other variables are fixed, right? So if as volume changes, du changes also. How much? This much. Round u, round v at constant temperature. Okay? As temperature changes, internal energy changes. How much? This much. Round u, round t at constant volume. Okay? Or we can say in another way that we simply take the total derivative of internal energy as a function of volume and temperature. You learned this from mathematics class, right? Total derivative of U as a function of V and T, and you get this expression. Okay? If you do this for an exact differential, you got two partial derivatives. Round U, round V at constant temperature, round U, round T at constant volume. Okay? Two partial derivatives. Although this is just a mathematical expression, these partial derivatives have very important physical meanings. We'll get to know that. Okay? Let's see. First, we know this, right? Round U, round T at constant volume. We already have learned this. This one is CV, heat capacity at constant volume, right? So among these two partial differential, we already know one, CV. So this one is CV. Okay. How about this one? Round U, round V at constant temperature. At constant temperature, how internal energy changes as a function of volume. Okay. That is actually defined as internal pressure, or denoted as pi sub T. Internal energy change as a function of volume. Okay. Why we call this as internal pressure is the unit of this variable, energy divided by volume, corresponds to pressure, right? Remember, pressure times volume is energy, right? That's why we call this variable as internal pressure. Okay? One very important meaning about this internal pressure is internal pressure is a measure of cohesive forces in the sample. It represents molecular interactions of real gases. Okay? You remember that for perfect gas, internal energy only changes as a function of temperature. That's the only variable which can change the internal energy of a perfect gas. Which means that as volume changes, internal energy does not change for perfect gas. You can see it from here, right? Internal energy as a function of volume. For perfect gas does not change. For perfect gas, only temperature can change this one. Okay? So which means that this represents the properties of real gas, intermolecular forces. Okay? And what kind of intermolecular forces exist? Repulsion and attraction. Remember, right? And depending on repulsion or attraction dominant cases, this internal pressure has different value, different sign, negative or positive. Why? Okay. Internal energy, if you recall the formal definition of internal energy comes from the total energy of kinetic and potential energies of molecules, right? Kinetic and potential energies of molecules. Okay? But here, pi t is defined at constant temperature. If the temperature is constant, kinetic energy is constant, right? Okay? Which means that pi t is dependent upon potential energy of molecules. Okay? Alright, so let's consider two different cases. When repulsions are dominant at high pressure, right? Remember? Molecules are close together. Repulsions are dominant, which means that molecules do not want to be close to each other, right? They assist expansion, right? Okay? Repulsions are dominant. In that case, if volume increases, what would happen? Those gas molecules would be happier, right? They don't want to be close to each other. So we make the volume increase, and they are farther apart. And they are happier, which means that their potential energy decreases, right? They get more stable. Those gas molecules get more stable, right? So when repulsions are dominant, internal energy decreases as a function of volume. The opposite case holds for attraction, right? When attractions are dominant, internal energy increases as volume increases. So, internal pressure round U round V at constant temperature, which represents the slope, right? So, in this case, the slope is negative. In this case, slope is positive. Okay? That's why internal pressure has different sign. Okay? Then, how can we measure this value, internal pressure? Can we really measure internal pressure experimentally? The answer is yes. People try to do it, actually. Joule. Remember Joule? Very famous guy, right? Very famous scientist. Joule tried to measure this internal pressure by doing some experiment. How? So here shows the experiment that Joule thought about, and by doing this experiment, Joule tried to determine this internal pressure. Let's first introduce this experiment. Experiment is really actually simple. There is a diabetic box. The box is insulated thermally from outside. Okay? And inside of that there is water. Here, water. And inside of water there are two vessels, okay, connected to each other. First, it is closed between these two vessels. At one side there is high pressure gas. The other side there is a vacuum. Okay? What he did was to open this valve. And then the gas would be expanded to the vacuum, right? Free expansion, right? And the Joule tried to measure the temperature change. This is thermometer. Temperature change associated with this expansion if the temperature of water changes. Okay? By measuring that temperature change, he thought that he could determine the internal pressure. Okay. Let's first see the result of this experiment. First, it is expansion, free expansion to the vacuum, right? So, work is 0, right? Total box is adiabatic, right? No heat transfer. Actually, not adiabatic. Sorry. He tried to measure the temperature of the water, but he could not measure any temperature change. Temperature did not change when he did the experiment. So temperature did not change, which means that there is no heat transfer, right? Q is 0, W is 0, Q is 0, which means that delta U is 0. If delta U is 0, internal pressure is 0, right? So he concluded that, internal pressure is 0, okay, based on his experiment. But actually, his experiment was flawed. he could not measure the temperature change, but there should be temperature change. The problem is he used water here, right? Water has very high heat capacity. So the temperature actually changed very small amount, but he could not measure it using the thermometer he used, because he used large capacity water as liquid. Okay? So anyhow, by doing this kind of experiment, we can determine internal pressure. How? Why this temperature measurement could determine internal pressure? Let's use the whiteboard. Okay. All right. Alright, so here's the expression for total derivative of internal energy, right? And this Joule experiment. For Joule experiment, free expansion W is 0. Okay? The whole box is adiabatic, so Q is 0, which means that delta U is 0. So for this Joule free expansion experiment, delta U does not change. Okay? Which means that du is 0. Okay? Then, if you rearrange this as a function of internal pressure pi t around u around v t would be minus cv around t around v at constant u. U is constant, right? U does not change during this experiment. Okay? So, if you want to know this, you can determine this if you know the heat capacity of liquid and this. What is this? At constant internal energy, you measure temperature change as a function of volume. That's what Joule tried to measure, right? He tried to measure temperature change as he does expansion, right? So if you can measure this, you can determine internal pressure of real gas. But Joule could not do it because his experiment had a limitation. But actually, there is this number. Temperature does change actually. Okay? So how does temperature change for real gas? We can do the experiment, or what we can do easily is that we use an example of real gas, a model system for real gas, which is van der Waals gas. Remember van der Waals equation? Van der Waals equation is the equation which is a model for real gas. Okay? Right? So, from van der Waals equation, you can calculate this. Actually, we cannot now. If you learn chapter 3, we can calculate this. So let's just see the result only. Using this equation, you can calculate this, and the result is very simple actually. Like this. Okay. So internal pressure for real gas, a kind of real gas, is positive. Okay? Which means that this part, which can be measured experimentally, is negative. Okay? Which means that if you do this Joule expansion experiment, as you do the expansion, temperature decreases. But Joule could not. There is temperature decrease, but he could not measure it. Okay? That's how we determine internal pressure from experiment. Okay. Right? All right. Actually, there is another way to get this expression instead of using total derivative. It's a mathematical way. It's actually using chain rule. You might remember this from mathematics class. Sorry. Using chain rule, you can also get the same expression. If you express chain rule for three variables, u, v, and t, you can get this expression round u, t, round v, round t, u, round t, round u, v, which should be -1. Let's look it up your mathematics textbook. Okay, if you rearrange this, you can get this same expression. Okay, so either way, you can do the previous procedure that internal energy is 0 for Joule experiment, or you can simply use chain rule using these three variables. Okay. All right, let's go back. Let's go back to the slide. So we learned about Joule free expansion. So we got the expression for du. du is equal to pi t dv plus dv dt. What if we want to know how internal energy changes at constant pressure? Previously, we expressed U as a function of volume and temperature, right? How about if you want to know how U changes at constant pressure? For example, if you want to know this, how internal energy changes as a function of temperature at constant pressure, how can you do it? It's simple mathematics, right? You divide both sides with dt, round t here, and take the constant pressure on both sides. Okay? You divide du with dt and constant pressure. You divide pi t dv with dt and constant pressure. You divide cv dt with dt, and you just remove dt, and you get cv. That's it. Okay? Here you have partial derivative, something like this. How volume changes as a function of temperature at constant pressure. Actually, it is denoted as expansion coefficient alpha. The definition of alpha is actually like this: 1 over v round t at constant pressure. Okay? So if you put this in here, you get this. Okay. round u round t at constant pressure is equal to alpha pi t v plus cv. Okay, which means that you can determine this if you know this information: heat capacity, volume, internal pressure, expansion coefficient, which can be determined experimentally, right? You can easily determine this one. Okay, it's easy. Let's consider a simple case. How about for a perfect gas? For perfect gas, internal pressure is 0. Okay, remember? Internal energy does not change as a function of volume. So if you put 0 here, then you get this one. Round u round t at constant pressure is Cv. Oh, you remember that round u round t at constant volume is Cv. Both of them are same for perfect gas. It's interesting, right? This one and this one are same for perfect gas. This expression will be useful in the next section. Okay. All right, we finished Joule experiment. How about enthalpy? We did through the interesting processes for internal energy. We do the same thing for enthalpy. Okay? We do the same thing for enthalpy, express enthalpy as a function of pressure and temperature. Not volume and temperature this time, pressure and temperature. Okay? Then enthalpy changes as a function of pressure, this much. Enthalpy changes as a function of temperature, this much. Round H, round P at constant temperature, round H, round T at constant pressure. Okay? It's interesting, right? So similarly to the previous case, these two partial derivatives also have important physical meaning, important thermodynamic meaning. Okay, let's see what meaning. First, this one, round H, round T at constant P, which is Cp, right? Cp. Okay, we already got one answer. Okay. Then how can we know about the information about this? Round H, round P at constant temperature. How can we determine this? How enthalpy changes as a function of pressure at constant temperature? Also, people try to determine this experimentally, including Joule. Okay? What kind of experiment? The experiment actually looks like this. Okay? Doing this kind of experiment, Joule and Thomson actually, Joule-Thomson experiment. Joule and Thomson try to determine that partial derivative. How? Okay. So let's look at this diagram. Okay. I'm going to use the whiteboard again. All right. So what we want to determine is this. How can you determine it experimentally? Okay. Okay. How can you determine that partial derivative? So Joule-Thomson expansion experiment looks like this. Looks like this. Let's first draw the diagram. Okay. Okay. the whole system is adiabatic. Okay, it's insulated. Okay, thermal insulated. Okay, what they tried to do was actually you first have gas here, P with P1 and T1. They try to push gas molecules inside of piston here. This is piston here, and there's another piston here. Try to push piston here, okay, through the porous partition. This one is either we call it throttle or porous partition. So it consists of very small holes, So they tried to do the experiment by pushing these gas molecules to this side, to the right. Okay? And during pushing, they try to do it slowly enough to maintain equilibrium. Okay? So this pushing is in mechanical equilibrium. Okay? And after they push it through very small holes, as a result, they would get expansion of gases to the other side, right? To the other side with different pressure and temperature. Okay? Also, during this expansion, during this compression and during this expansion, it's kind of imagining experiment. They try to do it slowly enough to maintain mechanical equilibrium during expansion, but not so slowly to be in equilibrium for the whole system. Okay? So, what would happen for the pressure during this expansion? Okay? Since we are basically pushing gas molecules through very small holes, you can imagine just like putting, like using hose with water coming out, and you make the hole smaller. What will happen? Pressure of the liquid, pressure of the fluid gets smaller, right? You get smaller pressure on the right side, right? Basically, pressure of the fluid changes. Okay? So from this kind of experiment, how could they determine this? How? How can they determine this using this experiment? So let's analyze the experiment in more detail. What kind of experiment is this? It's very complicated, right? So, the whole system comprising two pistons are isolated, adiabatic, remember? Adiabatic. So, for the whole process, Q is 0. You don't need to worry about Q. All you need to calculate is work, right? You can calculate work during first this compression from left side and during this expansion on the right side. How about first W1 during this compression? Since this compression is performed slowly enough to maintain mechanical equilibrium, work is minus P1 times final volume minus initial volume. Let's say P1, V1. Okay, this is P1, V1. Okay. How about during expansion? W2, the right side. also this expansion is performed slowly enough to maintain mechanical equilibrium. So it's minus P2, V2 minus 0. Okay? V2, V2. Okay? Alright. So total internal energy change during this process would be Q plus W according to the first law of thermodynamics, which corresponds to P1 V1 minus P2 V2. Okay? Which is minus delta PV, right? Okay. So if you take this to the left side, delta U plus delta PV is 0. Delta U plus delta PV is delta H. Remember, U plus PV is H. Huh. Interesting, right? This whole experiment is constant enthalpy experiment. During this whole experiment, Joule-Thomson experiment, enthalpy does not change. Okay? Enthalpy does not change. Okay? So, let's review this. You can read the textbook and try to understand this experiment, okay? It's rather complicated actually. Okay? So this whole experiment is constant enthalpy process, and from this result they tried to determine this. How? Let's go back to the first expression for the enthalpy. T, right? We started from here. And this whole process is constant enthalpy process, which means that this is 0. Okay? And we want to determine this around H, around P, constant temperature, can be expressed as minus, this one is Cp around T, around P at constant enthalpy. Okay? We can get the same expression using the chain rule. Okay? So, during this Joule-Thomson expansion experiment, what we could do is we measure the temperature change. We just measure it using thermometer as a function of pressure. You remember that pressure changes, right? P1 was larger than P2 if you do the expansion through very small holes. Okay? So you simply measure experimentally temperature change as a function of pressure, and you know the heat capacity, then you can determine this. Okay? Alright. Okay? And this experimentally determined value, round T, round P at constant H, is called Joule-Thomson coefficient. Or we denote this one as mu. Okay. Mu, Joule-Thomson coefficient. Okay. And this one, round H, round P at constant temperature, is called isothermal Joule-Thomson coefficient, which is denoted as mu T. Okay. Alright, and let's determine it. Let's calculate this. you cannot really do it using real gas. So similar to what we have done for Joule-free expansion, we use a model system for real gas, which corresponds to van der Waals equation. Okay, using van der Waals equation, we can determine this. Let's determine it. At first, let's consider a specific case. So we want to determine this. First, how about for ideal gas? For ideal gas, you remember that for ideal gas, U only depends on temperature. Okay. H is defined as U plus PV. Okay. Which is U plus nRT. Which means that also enthalpy only depends on temperature. Okay. So enthalpy does not change as a function of pressure. Okay, so for ideal gas, this one, mu T is 0. Okay. Don't need to worry about it. How about for real gas, van der Waals gas? So using van der Waals equation, you can calculate this actually, but we cannot do it mathematically now because we didn't learn something yet. So if you calculate this, mu T, you get this expression B minus 2A over RT. A and B are van der Waals coefficient. Okay? Which means that depending on the temperature, this number could be either positive or negative or 0. Depending on the situation, right? Okay? When this value is 0, if you calculate the temperature, T is equal to 2A over RB, and we call this temperature as inversion temperature. Inversion temperature, okay? And mu T is positive when mu T is positive. Where is it? When T is larger than inversion temperature. Okay. Okay. So since this is positive, which means that mu T is, remember, minus Cp mu. Okay. And mu is around P around T. No, around Tp. Okay. Around T, around P at constant enthalpy. Okay. So in this case, this one is positive. Cp is positive, which means that this part is negative, right? Because we have minus sign here. Okay. So, since during this Joule-Thomson expansion, pressure decreases, right? P1 is larger than P2. This one is decreased, which means that temperature increases. Okay. In this case, when temperature is larger than inversion temperature, if you do this experiment, Joule-Thomson experiment, if you expand gas through small holes, through throttle or porous partition, the temperature of gases increases. Okay. On the other hand, when temperature is smaller than inversion temperature, the opposite. Okay. Temperature decreases. Okay. And for most gases, actually almost all gases, this inversion temperature is really high. which means that normal temperature that we are doing experiment is the case of this. So if you do this kind of experiment for most gases, temperature decreases. Okay? Actually, you can see an example, very similar example. If you have a bicycle, and if you have a hole to the tire of bicycle, if you put your finger through that hole as the gas comes out of the tire, you can feel that it's very cold. It gets cold as the gas inside of the tire comes out, expands through this small hole to the atmosphere. Okay. All right. What we have got left? We basically covered most of the remaining section. Maybe one more. We already have covered this. CVCP. You can read the whole section actually. Let's see. We already have done this, how they do it, using this Joule-Thomson expansion, basically, which means that the gas gets colder, right? That's the actually principle of refrigerator, how they built refrigerator. Just read the textbook. It's not that important. Okay, finally, in previous section, you saw that Cp and Cv, if you compare both of them, Cp is larger than Cv, remember? How much? This much, for ideal gas. Okay? Why? We didn't derive it yet at that time, right? We can do it now, right? Cp is round H, round T at constant pressure. Cv is round U, round T at constant, actually volume. But remember that this one was same as this, right? From previous slide here. Let's see. Here, remember this? This one is same as this. Okay? So using this relation, so you can calculate the difference between Cp and Cv as this. Same condition, same constant pressure. Since H is U plus PV is U plus nRT for ideal gas. Okay, so you can put U plus nRT here, then you can simply get Cp minus Cv is equal to nR for ideal gas, not for real gas. Okay? For real gas, we can get much more complicated expressions, but I'll just skip that part. Okay. So if you want to know about the general expressions for difference between Cp and Cv, you can do the derivation. But I'm not going to go over this part. Okay. All right. That's the end of chapter 2. So, okay. You have learned many things. So if you want to review the whole chapter 2 and summarize it, let's look at the page 911 on the textbook. You can see the summation of the chapter 2 there. Okay, summarized diagram. Okay, so this is the end of chapter 2.